Hello, good afternoon. Welcome to the stream. We're here on another Sunday, and we are going to today, hopefully, finish up the chapter 2 of this book. We're working through this book, Essentials of Compilation, an incremental approach in Racket, except we're not using Racket. We are using Gleam. Gleam is a strongly typed functional language. It compiles to the Erlang VM. So if you have Erlang or Elixir or LFE or any of the other languages that compile to Erlang VM, you can use Gleam. And it's an interesting small language with very few concepts, but I think it fits itself really nicely to this because it gives us strong types so that we can understand that we have some safety around certain transformations we're doing inside our compiler. But it's also pretty lightweight. And if we wanted to, we could compile it to JavaScript as well. So it has multiple targets. And one thing that I'd like to do, maybe as we get further on in the book, we'll try to do this as a side project or as a break. And you may have seen this thing that is often associated with the Rust project, but I think it's also possible to use C++ and other things like that. But it's this website called Compiler Explorer, and you basically get a panel to put your source code in, and then it will run it through the compiler and output the format that you are concerned about. So like if you were curious about how a particular Rust program compiles into assembly code, you could have it output that, and it'll even go so far as to highlight sections that, if you're looking at a particular part of your Rust code, how does it end up being compiled to assembly? And some of that is just because the Rust compiler has the ability to trace that all the way through. Miss Spans, hi Chris, welcome to the stream. So that might be a nice side project. Is we can take our whatever version of Racket, like reduced language of Racket it is, and have a compiler explorer that runs completely in the browser. Thanks to the fact that Gleam can compile to JavaScript. So that is a potential side project that I've been thinking about, and maybe we'll do that as we get further on. Unfortunately, before the stream started, I decided, it's been a while since I've updated software, so Homebrew is running in the background while we talk. Okay, so last time, let's have a look here, and I'll go ahead and switch over to the code screen. Last time, what we did is we did this assign homes phase. So let's look at our commit history here. So we did a select instructions. We also finished explicate control. Remember, that was the one that kind of spanned the 2 weeks. Select instructions was about turning the kind of C-like language, which was assignments and primitive operations, into like an x86 assembly language like structure with variables. So this is, we have kind of holes that we need to give locations, and that's what the next phase was, is assign homes. So we did select instructions, and so we define this language x86 var, and then we translated from the CVAR program into the x86 var program, and that was fairly straightforward. And I remember specifically last week Isaac pointed out a problem I had with minus based on the order of the arguments. It's important. And then we were able to test that a particular kind of program in this CVAR language, which was a sequence of statements with assignments or return, turned into an x86 program with a single block. and then a bunch of assembly instructions. Now we're not actually seeing the the textual output of the assembly, but we have a data structure representation of that in this. Okay, and then we did assign homes, which was like take those variables and give it actual places on the stack. So we're not doing register allocation. That's chapter 3. We'll get to that hopefully next week. So this is just giving variables places on the stack for the frame of this particular function. And that amounted to looping over the instructions. And as soon as we find a variable, you give it that first place on the stack, and you increment the offset. So yeah, and then we're just doing some very straightforward translation, because these languages are almost the same, except that this one has a var and the other one doesn't. So we were able to just focus on how do we assign a home for a variable. And where did we put that? That was down at the bottom. Yeah, so it's like if this variable is already in our collection of spots, then we just return it. If it isn't, then we increment the offset and return the new collection of the new collection of locations for variables. So very typical FP stuff, always threading your state through. Let's quickly flip over to here. Oh, good. Okay, so that's fine. X is no longer available. Don't care. All right, so today we're going to work on the next phase is patch instructions. So this has one job. It's not too complicated. It amounts to the fact that x86, the instruction set architecture, or the rules of the instructions, say that you can't move from one memory location to another memory location. You have to go through a register. Which, if you think about the architecture, that makes sense. Like, you're really only accessing memory when you want to get it to do something. But with the way our compiler is outputting code right now, for example, in this assign homes test, where to go? So you can see that we're just putting all variables on the stack. So there are cases where when we'd want to move one variable or assign one variable to another, which was the original thing here, like, assign the value of x2 to y3. Those are all stack locations. So we have some situations where this gets moved from one stack location to another stack location, and that's not valid x86 assembly. So the patch instructions phase will go through and look for places where we're moving from one location to another, and it's going to replace that with move from that first location into a register, and then move from the register into the second location. It's really not efficient, but we're not doing any data flow analysis yet, so we don't know. We only know what the programmer told us, and if they're doing assign one variable to another, then that's what we're going to do. So we're not really concerned with efficiency yet. Okay, so let's go ahead and make patch instructions, and we'll make a new test for it as well. Test.gleam. Okay. So did I copy that? No, let's copy it out. Okay. So this is going to So they give an example in here, which is if you have like let A42 and you have let BA, oops, let's be consistent here, even though bracket is weird, B. So if you have a program like this, that's going to generate some, excuse me, that's going to generate some assembly that looks like move Q42. This is from the output of the assign homes pass that we did last time, RBP. Okay. And then it's going to move Q -8 RBP, oops, P to -16 RBP. Well, we can use this as a test case later, but we also have some other ones that we can write tests for. And this is going to be moving it to RAX because RAX is the return value of the expression, and then what they don't show here is that there's going to be like a jump conclusion. And this is start, but they're not showing that here. So the issue are these two instructions, or really this instruction. So what they want us to translate that into, and I'll just copy paste this. They want us to translate that into, we're going to cut that out and we're going to go move that into REX and move Q -16, or sorry, REX -16 RBP. Now you'll note that we have redundant moves here. Again, I said we're not doing any data flow analysis, so we don't know that from instruction to instruction that we could eliminate these two, right? We maybe later in the book, I don't know, but we might do some partial evaluation such that you could reduce this expression to let A42A, right? But we're not doing that. So what we want to produce from this phase is anything that looks like this from one stack location to another stack location turns into move this one into REX and then move REX into this one. So that's what we're going to do. Okay. So we need a pub fun patch instructions. And this is going to take a program. We've been calling it input, so I'll go ahead and do that. And we're going to need to import Lang's x86 int, because that's what we're working with. We'll call it x86. And this is going to take an x86 program. And it's going to produce a program. So we're not changing languages here, we're just massaging the one we have. Okay. So, what is the contents of this program? It has a body which is a dictionary of strings to blocks, and blocks are lists of instructions. So what we want to do is we're gonna do let body is input.body, and actually technically we are only going to have one of these, but I think that what we want to do is we need to import Gleam dictionary, and we're going to do dict map values. We'll say new body is this, And what is the syntax of that? Okay, so we give it the input.body, and then we give it a function which takes so this is the key we don't care about, and the block. And I'm going to make a new thing that says patch instructions block, and I'm going to pass block dot body. And then what we'll do is we'll do x86 program, and now we've got the new body. So we could probably do something like turn this into a pipe. Maybe we'll do that later. Let's make this function block. So we're going to have instructions is a list of x86 dot is it not instruction? Inster. Okay. I don't know why it didn't help me out there. And it's going to return a list of x86 inster. Okay. Oh, right. So we need to rewrap that. I'm going to pipe here. Right, so the types weren't lining up there. Okay, so here we are. We've got a list. Let's import Gleam list as well, because we're going to have to do operations over the list. So let's take instructions, and we're going to do list.flatMap. Why do we do list.flatMap? Because the problem here is if we have one instruction and we want to return multiple instructions, potentially, then we need to be able to return a list of them, right? So let's go ahead and make that. That takes a list and a function of an item to a list of items in another type. So let's make that function. And we'll probably unpipe that because we don't care. Now we could make a new function here, maybe. I actually kind of like that idea. I'll make this more compact. Patch instruction singular. Patch instruction. Let's go inster is an x86 inster, and this is going to return a list of x86 inster. Okay, and then we'll use the and it doesn't unpipe for me. Let's just put it in here and remove the pipe. Okay, I wanted to do this really focused because we have really only one case to handle. And what I want to do is this. So if we want to focus on this one case where we have a move and both arguments are derefs, right? So this is going to be move q. And what we want is this is going to be deref, right? Reg A. We're going to have to reconstruct this. So And this should be a very simple transformation. So we're going to do x86 dref. So we're going to move reg. And honestly, I wonder if there's a, Rust has that like at syntax. I wonder if Gleam has something like that. If it did, we could avoid reconstructing these. Let's look real quick. So docs, language tour. Let's see, contents. Look at case expressions. Variable patterns? No. Labeled arguments? No, that's so you can do like what looks like keyword arguments. Alternative patterns? No, so that's so you could match multiple things at the same time. Pattern aliases. Okay, so we could do as. So let's try that. As A. This is me learning Gleam live as well. As B. And then we can do A here. That's kind of nice. And B. That saves us, destructuring and restructuring there. We just use the dref as a match. Cool. Kind of like that. So I think we're actually done with this phase, believe it or not. Let's clean this up a little bit. Rather than assigning to a variable, I'm gonna get a little pipe happy here. We're gonna do this, and we're gonna pipe that here, because constructors are functions. So again, really simple phase. We're just turning this case of where you have a deref of both arguments on a move instruction, and we turn it into, take the dereference of that and put it into, put it into a register, and then move that register into the other deref location. Okay, let's write a test. So we're going to import Glee. Well, we don't need Glee unit. We need Glee unit should. We're going to follow. We're going to make use of this, these programs that we have in assign homes test. So this doesn't have two derefs in it in this one, but we do have it in this example. So let's do. And my cat is having a moment. Okay, patch instructions test. Okay, so we need to import Lang's x86 int as x86. And we need Gleam dict. Okay. So what we want is, I'm going to call this P1. And then we're going to copy this. And we'll say let P2. And we're going to go in here and we're going to replace we're going to replace multiple things in this one because you note that it moves from -8 to 24. No, actually, this is the only. This is the only one. Yeah. Hi, Isaac. Do you change back to your old name? So we're going to do P1 and I forgot we need to import passes, patch instructions. Okay. We're going to pass that to patch instructions, and then we'll say should equal P2. So this should fail right now because I haven't changed that. Let's go ahead and run this test real quick. Okay, so it's pub. I need to make it pub. Then it'll run it. Okay, so they were not equal. Obviously, we implemented the pass, but we did not write our test correctly. So let's adjust this test. So we know that this one, is going to be changed into, we're going to move into REX. And then we're going to move from REX into that stack location. Okay. Maybe it's smart to add this surf to the deref base of B is not EAX. Can you explain what you mean by that? The deref base of B. Oh, it was not REX. Okay. So what you're saying is that well, I would say I agree there in theory, but we're never generating derefs off of REX. We're only generating off of RBP. And I don't know what you would do in that case. Like we're not generating. Yeah, I do see the problem what you're calling out here. So let's put a note that this will not work if the register being dereferenced is REX. Should work off of any other register, but honestly, we're probably only going to use the base pointer or the stack pointer for derefs. That may change later in the book, for sure. Okay, so we have our test now updated. Let's run that. Okay, so it passed this time. We probably need to think of some more interesting examples to test. But this, this solves that particular problem. Okay. So let's go ahead and make a commit on that. And I'll use our handy Git panel again. I have just barely gotten used to this. So let's add that. And we have our patch instructions and our patch instructions test. So this is chapter 2.9, patch instructions. And we'll push that up so everybody has it. Okay, so our next step is actually very straightforward because we already, did the work, or they did the work for us. They say the last step of the compiler from LVAR to x86 is to generate the main function with a prelude and conclusion wrapped around the rest of the program. as shown in figure 2.8 and discussion section 2.2. So figure 2.8, I'm not going to be able to show it to the cameras, unfortunately. Says the start is the thing that we compiled, and then there's a main label. There's a .global main, and the main label does push Q RBP, move Q RSP to RBP, sub Q16 from RSP, and then jump to start. So basically that's saying push the previous base pointer onto the stack, move the value that's in RSP into RBP, so that's our new base pointer, and then subtract 16 from RSP. So it's like the why are you subtracting 16 from RSP? Because the frame in this calling convention has, you know, eight bytes above is the return address, which is technically what happens when you do call queue. The bottom of RBP is the old RBP, and then it's adding, in this case it's adding 2 slots for variables. So I think probably that's technically incorrect for us. We don't know how many variables we have, and they were mentioning earlier in the chapter that you need to track the size of your frame, and we weren't doing that. So maybe we need to go back and do that, and then our RSP we'll move it by the number of variables that we have. So let's think about that. But in the meantime, what we can do is we can, let's go ahead and make a pass, generate prelude and conclusion. And this is, I think the main thing here is that we're going to generate some text, right? So we need to turn our this into strings. So we're going to have to import Gleam string builder or string tree. And we will want to translate our abstract instructions into text. So let's go ahead and make a generate prelude and conclusion, and that's going to take x86 int x86.x86 program, and oops, need to capitalize that, and we're going to produce a string. Okay, so the way I would like to do this is I think what I'd like to do is generate main and conclusion in our abstract syntax tree. We'll add those to the program, and then we'll have a function that turns the program into text. So yeah, let's do that. So we'll have something that generates main. We'll say generate main, And we're going to pass it the input program for now. And maybe what we'll do later is, because we need to have additional information here, maybe the structure of these languages needs to change such that we can get the size of the frame, right? And I think that would happen in one of the passes that translates from x86 var into x86 int, maybe. Maybe in assign homes, we track that. And then I think that we were already doing that, and we just didn't have any way to annotate the program. So we're going to have to define what those annotations on the program are, and then possibly change that pass to insert that into the program. And we'll say let conclusion is generate conclusion. And then what we want to do is we want to take the body and we want to add main and conclusion to it. So we'll take input body and we're going to need Gleam dict. And we want to say dict insert. Main is going to get main. So we'll assume that main is a block, right? See, it's already inferred that correctly. Isn't that nice? And then we'll do dict insert conclusion, because this is what the function jumps to, conclusion. And then we'll say, we'll call it program to text. And I am passing main here because we need the assembly to have this dot global main in it. So when we get to generating the main text, we will put dot global main before it. Okay, so let's generate main. And let's make some assumption for now. This is going to take the program. Input. And it's going to ignore it for now, but we're going to return a block. And we'll do a to do here. So what is the contents of our main? As given an example, and I think we have it in one of these files somewhere. I saw it the other day. Where did we put it? All right, so here's what main kind of looks like. Note that this is the frame size, right? And that's so that if you had multiple like nested calls, or if you had some operation that translated into a push, you want to make sure that RSP is beyond the set of pre-allocated variables, right? That's what this sub 16 is for. So let's just copy these two things out and put them over here for now as reference. So for main, we want to do push Q, register, x86.rbp. Okay, and then we want a move Q from register RSP RBP. And then we're going to sub Q immediate 16, and this is the to do, right? And I'm going to put underscore here so we don't care about it yet, but we will eventually. Excuse me. Okay, so that's allocating the frame, and then we're going to have jump to start. And let's go ahead and do conclusion while we're at it. And it's going to have the same signature, honestly. And x86 block. And we're going to have add queue, immediate 16. RSP. And then we'll have pop, register, RBP, and we'll have return. Okay, so that's main and conclusion. And then we want to have a function, and we'll stub it out with a to do, because I think that we really want to go back and address this issue of we don't know how big the stack frame is for start. And that's something that we need to address before we go. And I mean, we can turn the program into text, that's fine, but let's go ahead, let's fix that next. And yeah, so let's stub out program to text. So this is going to take this is a dictionary, right? Because we don't care about the program contents yet. We just pass the body. So this is a dictionary of string to x86 block, right? And then it's going to take this is like the start symbol, which is a string, and we're going to produce a string. And so we need to, it needs to be qualified. Okay. Yeah, doesn't care about being used yet. Okay. So that's kind of the outline. And we need to go back and figure out what the size of the frame is. So let's go back into assign homes. Remember that this is collecting an offset, and it was, you know, it was being subtracted from each time. So we need to adjust the X. This is, remember, we need to adjust this. I don't think we care about it before this point. Right, because this is assigning, this is how much we know in this phase how big the stack frame needs to be. So x86 program in this file. Okay, so it has the body, and we're going to need to get, I mean, we could start with just a single integer, but I think that what we're going to want is like a structure. Let's call it x86 info, and I think that what we want frame size. There's a question in my mind of do we just do this, or do we do something like so that when we have more than one function, we know that this is the frame size for that function, for that label. I think let's go with this, even though it's a little bit cumbersome right now. We may have to revisit it later. Okay, so remember that like in the Racket version, they just have an associated list, and like in most of these examples, the info for that particular program type is just an empty list. Maybe added to the block, perhaps. The problem might be, I actually kind of like that. Let's look at assign homes. I don't hate that idea, Isaac. Yeah, that's an interesting idea. If we're going by the letter, what the book says, it's separate, but like we also diverge from it on primitive operations. We made variants for every primitive operation rather than having a structure that has some kind of like symbol in it, and then the arguments which have varying arity. We codified that. So I think this is a place where it might make sense to do that. On the other hand, our patch instructions phase would not modify that at all, right? And if it has to deal with, threading that through, maybe that's not so bad. Let's try that. Let's try that idea. So, frame size int. Let's do that rather than making a new structure. Okay, now all sorts of things are going to break, as you can see it here. So what do we want to do? We want to take this is going to have to return homes as well. Right, so let's have this return homes. And actually, it should return an int. And oh boy, no, that's right. Now we could probably at this point negate that. But we have an issue with this pipe, so let's see about unpiping that expression. Nope. Does it have to be on the pipe character? No. Okay. So let's do let instructions frame size and then we'll do x86 block instructions frame size. And we can just slurp that in there. Now this is going to break our tests. So the assigns homes test, the block is going to we're going to need to like track that, right? So and we still haven't negated that because it's it's a negative offset as we go through here. But what we should get is let's go ahead and correct that in assign homes. Oh no, wait, we did. Okay. So we know here. Where's the test? So that's is gonna have a stack size of 24, and then down here we need to look at this. There's only one variable, so and only -8 is referred to in there, so it should be 8, right? Okay. Let's run these. Oops, I'm gonna have problems with things being not compiled. Okay. Let's see if we can fix all of the compilation errors first. Okay, so generate main is going to have 0. Conclusion is going to have a 0. So you can see this stuff is kind of wide ranging. What other issues do we have? All right, so patch instructions. We're going to do, let's say new body is this. We're going to unpipe that. And then we'll say new body. Actually, we could have left the pipe in there. Let's leave the pipe in there. And we'll say that goes in here. And then we have block dot frame size. Okay. What else? Let's clean build. Okay, so we've got a problem here. And honestly, this is just that and just that. It should not change that field. Okay. So there's 4 warnings. Let's run Gleam test real quick and make sure everything is fine. Okay. All right. So now we know. We know what we need in these. We know we're jumping to start, so let's. This is the downside of doing it in. I'm gonna try to say this is the downside of doing it in the block rather than at the top levels. We have to dig down into the block, but we know that our main is going to jump to start. If they're going to use blocks or if-else branches, it might be problematic later, but expect the book to generate if-else in one continuous instruction string. Yeah, I would expect that as well. With labels and jumps is like jump EQ or jump Z, JZ. We'll find out later. Like I don't think control flow is for a while, so we'll have time to readjust that. But for now, we think of blocks as functions in the call return sense, and in that case, we need to be working with the stack as we do this. Now, interestingly, conclusion. I guess it can't be reused if you had multiple functions because this is dependent on the frame size. But let's get that frame size out here. So we're going to say frame size is going to be input.body. So we need to do dict get. And we'll say we're going to do let assert okay, block start block input.body start. Okay, if you haven't seen this, I actually saw this the other day. I was like, oh yeah, we have that. This will essentially panic if you don't have like if this returns error, which is a simpler way than what I was doing before in other parts of this code. So we're going to say start block.frame size here. And we'll do the same thing down in the conclusion. Okay, and then we'll use start block.frame size. Okay, now I feel like we should potentially have another phase, and maybe what we do here, rather than return a string right away, is we return an x86 program. I like that idea. Then we can verify the data structure in our tests. And we can make this program to text public. And let's say entry. And then we can test that separately. Okay, so we're not going to do program to text. We're just going to reconstruct a program. And that's fine. We don't need that yet. And that's it to do. So let's make a test. Generate prelude and conclusion. Oops. Rename that, please. Test. There we go. Okay. And we'll do the same stuff we did before. Test. And we're going to have to import some languages, so let's just go ahead and get that stuff. Oops. Yeah. And we're going to do passes, generate prelude and conclusion. And we'll go ahead and import that even though we're not using it. Okay, so let's take something from the last phase. What did I modify there? Oh yeah, I had to add the frame size. So let's take like this. Oops. Copy this whole thing. And I think the last thing that we will do for this chapter is we'll go into the top level compiler thing, and we will link up the phases as they should be. So so that we can like pipe from one to the next, which will be super nice. Okay. So what we want is we want basically the same program, but we want to add main, and that's going to have 0. We'll figure out what that should be, and we want to have conclusion. And this is going to be very, rote stuff, but here we go. So we know that what we want to generate is push Q, and here I am typing this again, but bear with me. I don't want to copy paste. I want to like think about what the difference is, and encode it in the test with static stuff. So RVP. One thing that'll be fun to look at is sorry, let me continue typing this. We know in this case the frame size is 24, so that should go there. And we're going to jump to start. Okay, so there's main. Let's do conclusion. What I was going to say is what's fun, at least for me, in a lot of this is look at the code that's generated. One thing that has really been neat about reading the code that the Erlang code that gets generated is that all of our languages, since they have no functions in them, they're just like dialyzer types. There's not even like records or anything like that. Now it'd be nice if the Gleam compiler could emit records for Erlang interop, but that requires, you know, include files and whatnot. But we don't really need that. Okay, so the conclusion needs to add queue, and here's our stack size again, 24 to x86 register RSP, and then it does pop queue. Oh, pop queue. Thank you. RBP, and then does retq. Okay, so that's what our output program should be. And so let's do our pipe test here. Generate prelude and conclusion, and should equal P2. Okay, so that test pass. It's complaining our program to text doesn't work. That's fine. So before we go and write the program to text function, let's go ahead and write the test on this one, because I think that this is, now that we have this, so we're going to say this is the program, and then let's write the program text. It's just complaining about it not used. So we'll leave this blank for now, but let's go program to text. And we should change the signature of that. This should take an x86 program. That'll make our test easier to write. And main is the entry point, and we'll say should equal text. Okay, so this is gonna, oh, there's a double quote. Okay, I thought it required triple quote. Let's look here. Strings. Okay, so multi-line string, you don't actually need anything special. So let's just do it like that. Okay, and here's what, let's look at this, and the problem being I don't know the order this is going to go in. I suppose we could force it to go in alphabetical order. Okay, let's assume it's going to go in alphabetical order. So we're going to have conclusion. Hi, Amos. Welcome to the stream. Okay, let me hide the shell here. So we're going to expect, this is going to be add Q 24 to RSP. And then we're going to have pop Q RBP. And we're going to have write Q. And then we're going to de-indent. And next will be main. And we want to, if we're following syntax, actually this has, is that 4 spaces? Let me see. I don't think it matters that much, but why is it 7 spaces in their output? Kelly just heard you say that and then asked, can he hear me? No, I can't hear you, Kelly, but Amos, if you want to relay messages, I'm happy to answer. Okay, so we need this .global main. And I'm going to put an extra return between these things because I think that's going to make our output look a little cleaner. So we're going to do 4 spaces again, and this is going to be push Q %RBP. Let me collapse this for now. And conclusion, I want to be able to see main. All right, so push Q RBP, and we're going to have move Q RSP to RBP, and we're going to have sub Q RSP. I'm sorry, that's backwards. Sub Q 24 RSP. And we're going to have jump start. Okay, and we'll do another double return, and then we'll have start. And that's in our case. Let's collapse these, and we'll show start again. So we're going to do move Q 20 into -8. And this is again is just about outputting the AT&T syntax of the assemblies so that we can actually use a command line assembler to write it out to an object file. Okay, and 22, -16% RBP. And what we'll do after this is we'll write tests, or we're writing the tests. We'll write the code that generates from our abstract syntax tree into the concrete assembly syntax. Okay, and we'll do move Q -8 RBP into RAX. We'll move Q RAX into -16, -24 RBP, and then we will do, one thing that we didn't handle, I'm not sure if it's an issue. They definitely said it on moves, but maybe patch instructions needs to handle this. I wonder. For now, even if this is incorrect, let's go ahead and generate it, and then we'll go back and fix patch instructions, I think. I'm missing $1 in line 132. You are correct. Thank you. Oops. Okay, and then, so where are we? So we moved REX into that. Yeah, and then we have add Q, and this is the thing I think is wrong. -24. Yeah, I think that should actually be move this into REX and then add QREX to that. And then okay, so this is what that was kind of tedious, but this is what our program should look like when it's written out to text. Okay, obviously this is not going to pass because we have a to-do and it panics. Right. Okay. Yeah, let's go ahead and do this bit. And what are we going to do? We're going to use, I think we're going to use string tree. I had imported it before, but we weren't using it. So we're going to make a new string tree. And why do we do string tree? It's a more efficient way to build up strings. So let's look at the docs for that. Gleam standard lib. Yeah, here we go. We can start there. String tree. So appending is like constant time. It's super important. So you can append individual strings. You can append entire trees. And then, so what we'll do at the end here is you can join trees with separators. That's going to be super useful. You can prepend, and then finally at the end we'll do toString. So whatever our pass looks like, let's just say this, and that's not going to be what we do, but let's do toString tree. That'll be the last step in this. Okay, so in order to have this consistent output, we need to map over the dictionary in the order that where the symbol, the label, is lexically sorted. So let's look at what we have in dictionary. Dictionary. So there's no guarantee, because this is using maps underneath, right? Yeah, the tuples in the list, if you go to list, have no specific order. So if we can do list, is key sort not imported? Do list sort. Yeah, this is gonna be inefficient, but I actually don't. I'm not concerned about it. Does string have a compare function? It does. Okay, and he has this nice type less than equal greater to. Okay. So we can do I think what we want to do is go input body, and we're going to dict to list, and we're going to go list sort, and this takes a function. So we want to do string compare. We want that to be the eventual function. So let's just write it out. I'm not sure that I can do the kind of composition I'm thinking of here, because these are pairs. So let's just do it the hard way. We'll do string compare, pair dot first A, pair dot first B. Okay, can we import that? Okay. So that gives us it in order. We'll say segments. So this is going to be, or we could call it sections. I don't know. So we're going to do this. And then we want to do, let's make a block to text function. And those should return string trees. And then I think what we'll do is we'll do join sections with, you know, blank lines, right? Because we wanted blank lines in the output here. I don't know that it's, yeah, I think what we'll do is we'll do join each of this. So like it'll start with the label, and then we'll have the instructions, and they'll be joined with slash, you know, with new lines. Yeah. Okay. And this is, we're gonna need to pass the entry so that when we get, you know, a pair of where, you know, the entry is this, we generate that global symbol. Okay. And I'm sorry, this needs to do list map. My bad. And this is going to be pair. And we will do let's just do it like that. Actually, I can simplify that. And then we can combine these. We don't need to have the let anymore. And we can have string tree to string as the last thing. Okay. I'll do partial application there. Okay, so fun block to text. Okay, so this is going to have the second argument is going to be entry, going to be a string. And what we want to do is return a string tree dot string tree. Okay, and then our key value pair is going to be a pair of string and x86 block, right? Okay, so now there's no type errors up here, and we just need to label block KV. Okay, so let's do let tree, and we're going to say entry equals label. There's not, I don't think there's an if in the language. Yeah. Yeah, there's no if, so we have to match. So we could do case entry and say if it equals that, then we want to do a string tree from string, and we wanted to do 4 spaces, global, and a space, and label. Otherwise, we want to do string tree new. Oh, okay. So I forgot about this a little bit. We could do it a different way. We could do, you know, like I was starting with. That might make more sense. Then there's not this extra business. True or false. Okay. So now we have a base tree. And we want to, now we want to add the label to it. So there's a question in my mind if we're just building a list here. Maybe we don't need this initial. This is like, maybe this is not tree, but this is let's say lines. So we're going to do label and we'll append that. And this is going to be what we do here as well. What I'm trying to do in this case is yeah, it's not used. What's the complaint about? So we have list of string tree. This is list of string tree. What's the problem? Hi, Cameron. Good to see you. Oh, it's complaining about I'm not returning a string tree. Like what we want to do at the end is like concatenate the lists. So let's call this prelude, and then we're going to say instructions, and we're going to map over the instructions of the block. So let's do block body list map, and we're going to say we're going to make a function instruction to text, right? And we can actually skip the bit here where we're piping, because this is just gonna right. So this is gonna create. No, actually, we do want a pipe here. We want a pipe here because we want to add the new lines. Or do we want to do that at the end? Here, let's do it at the end. Figure it out. Okay, so let's take prelude and let's concat. Is there list concat? List append? Yeah. List append instructions. And then that's going to be a list of string trees, right? So then what we want this to return is a single string tree, and we're going to do join with new lines. Okay, we're getting there. Like this, this sort of code is always fiddly, but let's go ahead and implement instruction to text. So this is going to take an instruction, or abstract instruction type, and it's going to return a string tree. Now, it's not strictly necessary that we do this. We could just do plain strings, but I think that this is going to factor out pretty nicely with as a recursive algorithm here. So yeah. So we need to do a case on instruction and have it fill out all. Did I not? What's wrong here? Why were we not able to fill out all the patterns there? Add missing patterns. Oh, well, helps if I type the thing correctly. Okay. So we want to basically fill in all these. This is label arity, jump symbol, A and B, argument A, pop Q, push Q, ret Q doesn't do anything, sub Q, A and B. Okay, so we're gonna let's prototype the add Q, and then we'll do the rest. We'll do the same for the rest of them. So we know that we want I kind of feel like we should be building this as a list of string trees and then call concat at the end. Let's do that. And since these are all like in that syntax should be indented, let's make a function that just returns indent, returns a string tree. And 4 spaces. and there's our indentation. So then we can go indent text, not 3 dots, 2 dots, because reasons. String tree concat. Is it concat? Yeah, here, leave the to do in there. Yeah, so that takes a list of string trees, and yeah, okay. Okay, so what I want to do here is we want to return a list, and this is from string, and this is where we're putting in our instruction. And then we will have, let's say, arg to text, right? And we'll pass a, and then we'll have the static string comma space, and this will have a space in there, and then we'll have arg to text b, and we'll fill out all of the comma. We'll fill out this function next. Okay, so let's go ahead and fill out the rest of these. Call queue. I think this arity, we're not using it, so we just need the label. And let's do this one a little bit simpler. We'll do we'll append label. What's wrong there? Oh, we don't need that. Okay. And jump is going to be similar to call queue. So let's just copy that. And this is going to be jump. All right, and move queue is going to be basically like add queue. So let's copy that. You know, a lot of things in this are going to be very similar. Okay, and let's do the same for sub queue because it's basically the same. And this one is string tree from string, red queue. And now we can do all the single arity ones because they're going to be not that different from this. We'll do queue. Just no. Why does it not give me unpipe? I thought that used to be there. We'll manually unpipe some of these, I think. Let's go ahead and do this one. Why do I do pipes in some cases and not pipes in others? Personal preference. I think like this one is bigger, like there's more steps to these 2 argument instructions, so it feels like you want to kind of see that spread out, but like where there's just one, it's not so important. And actually this one could be even simpler. We could join with space. Okay, so let's do this and change it to pop queue, and again push queue. I'm not being really consistent here. We could probably make functions that are like, you know, 1 argument instruction or 2 argument instruction, and or like break that out even more. Okay, so actually this is not a list now. It's just a single string tree. So let's implement arg2text. So this is going to take x86 arg, and it's going to produce a string tree. Okay, let's add the missing patterns there. So here we have, what is that offset? Let's move that down. I want to do the simpler ones first. So immediate is going to be a value, and we know that that is going to be from string, and we have the $, and we're going to append int to string I. Okay. For registers, we are going to have to make a mapping function from string reg to text r. Okay, and we're making this so that we can reuse it, right? So the deref instruction or argument is the register first and then the offset. So we're going to let's concat, and we'll do a list here. So we know that this is the register and this is the offset. So we want to do from string int to string of offset. You know, there's lots of ways to do this. I was starting with concat because I was thinking of it as a list. But we could start with that, and then we'll string tree append, and give it, you know, the open that, and then we'll do append tree reg to text of r, and string tree append close parens. I'm gonna have to probably spend some time making these consistent. Like, do I use pipes? Do I not? You know, do I use lists as arguments? Like, there's all. Do I use trailing parens where they're not necessary? There's all sorts of things there that I need to make consistent. So let's convert register to text, and this is going to be x86 register, and that's going to be a string tree. Getting to be the end of the stream, isn't it? Yeah, 20 minutes. Okay, so let's match all the register types. And then we're going to do interestingly, I think a string tree is oh, that's interesting. It's opaque, obviously, but it's actually just an IO list underneath. Yeah, see, like it's calling IO data append. Okay, that's interesting to know. So for we're gonna do this. R. So all I want here is what is, note that the registers have to have percent in front of them. So I just want to turn these into the lowercase names of these registers. Obviously we're not using most of these. We're only using this base pointer, the stack pointer, and the accumulator. But we specified this early on, so we have to make sure that we do the whole thing, for better or worse. And hopefully in the next chapter, we will start to make use of some of these registers as opposed to doing everything on the stack. There's maybe a more efficient way to do this with some like dynamic or something, but this is fine. I'm not worried. Okay, so let's have a look at our test. Probably gonna break. Let's see if it passes and what we get. Okay. Okay, so we got a problem there. We have a type issue. Let's fix that. Where is it? Okay, so we actually, this just returns a register. Or reg to text returns a register. So okay, values were not equal. Yeah, we can deal with that issue of call queue that we don't care about what the arity is. Okay, so there's a problem here in that we expected we should not have expected conclusion to be right. So we need to adjust how our test is written. We don't want that initial thing. And that's because we're using the multi-line string, and then we need that to end like right there. Okay. Actually, let's put that back, because I think that if you don't have that indent on your multi-line strings, let's do string trim. Because we're not going to be having trailing new lines or initial white space. Okay, so looks like we have an indentation issue. We have 4 spaces there. we have too many spaces in our generation. So 1, 2, 3, 4. Is that what we had before? Let's run it again. Okay. So this is what, those are 4 spaces there. 1, see, 1, 2, 3, 4. And this is generating 1, 2, 3, 4, 5, 6. I wonder. So the thing that is interesting about this is we have the expected is actually the output of our code generation, of our text generation. And here is what the test fixture said. And I'm not sure why this has fewer spaces when we have 4 here. We do have indentation there that we shouldn't. So let's look at what I got wrong. Okay, indent. Oh my goodness. That must have been something exciting going on downstairs. I don't know if you heard that. Okay. Okay, so our indentation is happening on individual instructions, but it's not happening on the prelude, so I'm not sure why we are getting... expected is not the multi-line. No, it's left and right. Or is it? I wonder if it's just an issue of we need to de-indent that in the test. Let's go on your hunch here, and see if I remember how to do that. Yeah. Okay. Let's remove the extra spaces here. Oops. Okay. Sorry, I did an Emacs key combo there and it screwed me. We just want to delete that. Okay. Let's see if that fixes it. No. Okay, so it's still broken. It's still incorrect, but we at least got something different. Okay, so now they're lining up as far as the indentation of instructions. Where are we breaking? So there's 2 new lines there, and we only have 1 here. So let's add that new line and add that new line. And thank you, Isaac, for calling that out. I thought, yeah, entry between block are gone. Okay. What? Did I not just change that? Okay. Yeah, there's an additional new line there. I wonder... if I need only single new lines. Okay, now that's lining up there. Um, we're getting 2 new lines after global. Why? Int the test. What do you mean? Like put a breakpoint in it? The test is wrong. Yeah, I'm just trying to figure out where. Oh, this. It needs to be hugging that. Like so. Yeah, that was the problem. Okay, so we're still not lining up there. Do I need to? I need to put that back. The double new line. It was just in the wrong place. Okay. Whew. That's fiddly. Honestly, I probably should have made this a separate file that we read in as a fixture. But there we go. Okay, so final thing that we're going to do today is we are going to change our compiler Gleam. So we're going to make a program, and we're going to pass it through all the passes, and then we're going to print it out. I would love to assemble, but I've not prepared us to actually build the artifact. I just want to have it print out the assembly. I love green test too, Amos. Yes, we all do. Okay, so we need to start with lvar, basically. So we're going to import langs lvar as L. So let's look at maybe some other examples in here, and maybe we could start with something like something that we were testing that's kind of complicated. Those early ones are not complicated because we're using a much simpler sample language. Okay, I don't know what my wife is watching. I guess she's watching the soccer game. That's why she's yelling downstairs. All right. Well, we could do. What was that one? Yeah, let's do that program. We've used in tests a bunch, and it actually should be what the output of our of this is, right? So let's build that program from scratch. Okay, so we're gonna make a program, and it's gonna have a let, and the let is going to be bound to y, and the expression is a let, which binds x to 20, and then does a primitive operation plus var x, with another let. And this is that rebinding example that we looked at earlier. 22. And it's just returning that. Yep. And then let's see, make sure that we're so finally we need var y. I think this is it. And I think that we can probably look at one of these tests and see this. I don't know if we did this example. No, it's similar though. Okay. I think that this one came in the explicate control, like this is, but this is with uniqueified and it's in a different language, so we can't really use that. It's not really remove complex operands. So let's just go with this. So this is our program. So we are going to take P and we're going to pipe it to uniqueify. And then we're going to pipe that to, make sure I get the pipeline correct here, remove complex operands. And then we're going to pipe that to explicate control. And then we go to select instructions. And then assign homes. Excuse me. And then patch instructions. And then prelude and conclusion. I called it generate prelude and conclusion. And then we'll have program to text. And then we'll have io dot println. What's wrong there? Oh, this needs the entry symbol. Main. Okay. Let's see, Gleam build real quick. Make sure everything is fine. Gleam run. Okay, so we went from this program all the way to assembly. So let's look at what it output. The stack frame is size 32 on this one, apparently. We do need to still fix that. I think that we can maybe take another half hour or so and fix this particular issue. But we can see main does what we expect. The conclusion unwraps that stack frame and calls return. And then, you know, our start, looking at our program, moves 20 into that spot, moves 22 into that spot, and then moves from that spot into REX and then over into 24. And then it's taking this and putting in REX. So we have the variable we assigned 20 here. And then it's moving it into another spot, and then it's adding, right? Adding 24, which was from 16, which is 22. And then finally moving that. So again, it's not efficient code. It's not really that good assembly code. I would, you know, in this case, I would love to see this flattened down to, you know, and this would have to be involved in partial evaluation, of course, to get it to that. Data flow analysis, I mentioned multiple times, but I'd love to see it go move Q20 into REX add q 22 to rex and then jump. That would be the most efficient thing. But since we don't really know what these variables are for, the programmer, intention there is not obvious, and our phases don't handle any of this. So there's no code action for, yeah. Okay. So let's go ahead and add everything, I think. Stage all. And this is 2.10, generate, prelude, and conclusion. We'll go ahead and commit that and push, and then I think we need to fix the instructions where we have two derefs that are not just moves. So I think that's the main thing that we need to deal with right now, and then yeah, so let's figure out what other instructions need to deal with this. There's a question in my mind as well, whether unary or like single argument instructions need to have a register as the argument. That much is not clear to me. But let's go ahead and fix all these two argument instructions. And we'll do this. And this will be add q. We don't need a comma there. Sorry. That is my tendency to do Rust-like syntax. Kind of throws me for a loop. Okay, so add q. We need sub q. And why don't I just copy that? This one will be slightly different, and we might want to write a test for this, in that because subtraction is not commutative, we need to move B into the register. Is that right? No, we move A into the register and then we sub B rather than the other way around. Does that make sense? We want to subtract B from A. Or no, this is subtract A from B. Or like the target is always on the right. Anybody who knows x86 assembly much better than I, please advise, because I'm not convinced that even this is correct. And maybe it's just my time doing, in college we had a microprocessors class. We built the board, we wrote assembly for it, and it was an 8-bit Intel processor, the 8051, and which is a great little microcontroller, but it was your arithmetic operations, the result always ended up in REX, except it was just AX because it was 8-bit, right? So I think that, I'm not sure that that's how the architecture works on 64-bit x86. Let's go ahead and just fix this then. Yeah, you did 8051 in MIPS. Sorry, yeah. 8051 is a great little platform. Okay, so we want to subtract A from B. So this is still correct. You know, it's basically this. All right, what other instructions do we have that are to argument? Move, sub, add, call queue doesn't count. These we don't have to move. Push queue and pop queue, you don't have to move anything into a register first. Neg queue, I don't know. I think it's only for these three. All right. So we're going to run the test and it's actually going to fail. So that'll be interesting. Okay. So what we expected had this in it still, but instead we've inserted the move and the add. So we need to go back to our test and fix the expectation of the test. This, we're going to take A and move it into REX. And then we're going to subtract. Oops. Let me put that back there. Okay, now it passed. That was kind of subtle. And given that we don't have the instructor materials for this, I'm a little bit concerned that what we generated is still not correct. But let's run and see. We should not have any of these where we have two derefs in them, any instruction. Right, so this one has a stack location and a register. And a register and a stack location. A stack location register, register stack location. Stack location register, register stack location. And then the stack location to register at the end. Okay. I don't know if there's any sort of like x86 linters or anything like that online. That might be something to search for later. But this is a good place to wrap it up. So why don't I make a final commit for this chapter. And we're going to say fix patch instructions to handle other two arity instructions. Okay, and that's a good place to stop for next time. I'm really excited about next time. You know, we could do the challenges at the end of chapter 2, which are about doing partial evaluation for LVAR, which could yield us some optimizations. But we might just skip that because I think like chapter 3 is going to be really exciting. It's register allocation. And I don't know if any of you have tried to write a compiler before, but register allocation is like the craziest thing that like I never understood. When I did compilers class in university, it was all front end. So it was all lexing and parsing and a little bit of semantic analysis. And we didn't do like the bottom up. I really like the approach in this book. I'm really enjoying this. I hope you are too. And I'm going to continue. We'll learn register allocation next time, and we'll get going on it. and produce some hopefully interesting stuff. So, all right. Thank you so much. And we'll see you next time.